Okay, good morning, everybody. I hope you are doing well. I hope you had a good weekend and a good test number one. By the way, I uploaded I created a poll in the lab meeting channel asking you for your scores in test number one, just to give me a rough idea of how you how you did in the exam.
Uh, the
The yeah, the exam covers problems from Cal 1, and that's still important because most of the topics in Cal 2 requires a good knowledge of topics from Cal 1. So I hope you guys drop your scores there. It's an anonymous poll, so don't worry. Your score will not be broadcasted to everybody. But yeah, just to give me a rough idea of how you are doing, and I'll do that for every after exam, so I know I can at least track your performance in class. All right. So also, I have learned today that you finished the discussion on using the methods of disk and washers for computing areas of solids of revolution. So we'll do a couple of examples on that. Plus, I guess last week you already done setting up integrals for the volumes of solids with known cross sections. So I'll start with that, maybe a couple of examples, then go to solids of revolution. But I received a problem from one of you guys over the weekend, so maybe I can discuss that. It's about average values, but I guess this is a good problem for everybody, for your preparation for the second test. So, or probably some of the written homeworks that you still have to submit. So I hope you guys can see my screen because I guess last time we had some troubles with this. So just quickly, so the problem goes this way. So we suppose that we know that b is a positive number, and the average value of the function f is 1/6 over the interval 0 to b, where the function f is the linear function 3x minus 5, and we need to find the value of b. Well, for for word problems like these, we want to first be clear what is being asked. So in this particular problem, that's easy. We're just to look for the value of b. And then the next is, what are the given facts? What are the information that are made available in the problem that relates to finding the value of b? Well, we know that b is a positive number that might come into play later. And then we know that the average value of the function f over the interval 0 to b is 1 over 6. So basically, from there, we can deduce that f ave is equal to 1/6. But remember, the formula for the average value is 1 over the length of the interval. The given interval is from 0 to b, so the length would be right endpoint minus the left endpoint. And then integral over the interval of the function f, so which is 3x minus 5 dx. Okay? So basically, this tells us that 1 over b, integral from 0 to b of 3x minus 5 dx is equal to 1/6. Good? And then from this, we will try to see what is the value for b. Well, how do we find a value for b? Well, we need to evaluate this integral so that we will have a simpler equation to deal with. And that's not that hard because, the integrand is just a linear function, so I can do the usual integration techniques that we have learned from Cal 1. So I'll just copy the constant 1 over b here, and then integrate. This would be 3x squared all over 2 minus 5x evaluated from 0 to b equals 1 over 6. And then let's carry on. It's going to be 1 over b times, I'll plug in b into the x's. So I'll have 3b squared all over 2 minus 5b, and then minus 0 equals 1/6. And then we'll have, okay, I can cancel this b. So I'll have 3b over 2 minus 5 equals 1 over 6. And then I'll add 5 to both sides. So I'll have 3b over 2 equals 31 over 6. And then I can multiply both sides by 2/3 so that that 3/2 in front of b will go away. So this would be 62 over 18, or this is 31 over 9. Okay. I hope this is one in the options. I guess the answer was 14 over 9. Did I do some arithmetic errors here? Let's see. Can you guys spot?
9 is an answer choice for that problem.
Oh, come again, Robert? I didn't catch
13
that.
over 9 is an answer choice.
Mm-hmm.
Yeah.
31 over 9. Okay. All right. So I hope I did arithmetic well because I thought you got the right answer, which is 14 over 9.
Oh, no, that was a guess. I screenshotted it when I was doing it because I didn't have
Okay, yeah. It has a green marker in it, so I thought it's the correct answer. But I think my arithmetic is good, so it's 31 over 9. All right. Does that make sense? I guess what made it look complicated is I guess you already had this set up, but it is almost always intimidating to see the unknown appearing in one of the bounds for the integrals. So the key there is don't get too much intimidated or baffled with the problem. Try to think of what would be the next step. Well, I have an integral over here. B is a constant. It's not a variable. So I can do the integration by just pretending that B is any other constant and then try to simplify the left-hand side, and eventually you see, oh, this is just 3B over 2 minus 5. The right-hand side is 1/6. And then I can solve this using elementary techniques from algebra. But I understand what have caused the difficulty here. It's just the problem looks intimidating. Okay. All right. Is that good? Well, if that is it, if that is fine, then let's go to the topic at hand today. Have you guys seen the updated version of worksheet number 3? I guess from last time we answered the 4 or 5 problems from worksheet number 3 pertaining to area. We haven't we were not able to discuss some of the problems for area, but I included the solutions to all of them in the annotated worksheet. So okay, so if you haven't seen it yet, so we stopped here last time for problem number 9, but we skipped some problems. So what I did is to just include the detailed solution to those problems that we were not able to discuss. So you can see it there when you download the annotated worksheet. So the point here is for you to try those problems that we didn't do together and then compare your answers with the one I had uploaded in the annotated worksheet. So I hope that will motivate you to try to answer the problems, because when you get stuck on a particular step, you can take a peek on my answer and see what should be done next. But the idea is for you to understand the process and try to do these exercises on your own, which will be a good practice for upcoming exams or quizzes. Okay? So with that out of the way, then we can go to computing volumes. Unless you have some questions. One of the comments I got from the poll about the lab so far is that I guess some people are having difficulties reading my handwriting. I apologize for that, but um, I guess I cannot do anything more about that. But what I do during the lectures or the labs is I usually read what I write, or I write what I say. So kindly pay a little bit more of attention when I am writing or speaking. Or if you don't, if you cannot read anything I write, just let me know in the chat, or you can raise your hand and then I'll recognize you so that I can clarify things out. Right. So now, computing volumes. There are two types of volume problems that you discussed in the lecture. The first one would be computing volumes of solids with known cross sections. and bases. And then the other one would be solids of revolution. But perhaps I'll start with some examples about solids with known cross sections and bases. So the idea here is you will be given two information, or at least two information about the solid that you want to compute the volume of. You will be given how the cross section looks like, or sorry, first how the base looks like. So I suggest you draw at least a rough picture of how the base look like. So perhaps say you might be told that, okay, this would be the base of my solid, right? So let's highlight this. This is the base, the region R. Of course, this will be given by some function y equals f of x. Usually you have the x-axis, or sometimes you have, say, y equals g of x over there, okay? And then aside from the basis, or the base of the solid, you will be told how the cross sections look like, right? So the idea here is that the cross sections could either be perpendicular to the x-axis or perpendicular to the y-axis. Well, if the cross sections are perpendicular, so I'm going to use this notation for perpendicular. So take note for the rest of the class, when I write something like this, that means perpendicular, right? So if the cross sections are perpendicular to the x-axis, then you will use dx, okay? On the other hand, if the cross sections are perpendicular to the y-axis, then the variable of integration would be y. That will always be the case, okay? And then say here, I know that for this particular example or illustration, say the cross sections are perpendicular to the x-axis. So that means you will have vertical strips over here. So the volume will be given by an integral with respect to x, because I assume here that the cross sections are perpendicular to the x-axis. So I need the bounds for x. Say the region started at x equals a and ended up with x equals b. So the bounds will be a until b. Then what's the integrand? Well, since we are dealing with volume, the integrand will not simply be the height of the vertical strip, but would be what? This would be the area of the cross section. And this area will be given in terms of the variable x. So it is important to take note how the cross section looks like, right? Usually you will be given special objects or special shapes for the cross sections. I guess for Cal 1, the usual choices would be squares, semicircles, or perhaps the hardest would be equilateral triangles. But say you have squares as your cross section, so you can imagine having squares that are sticking out of my screen. So basically, and I will ask for your imagination here because I'm not good at drawing three-dimensional objects. So basically say if the cross sections are squares that are perpendicular to the x-axis, so you will have squares that are sticking out of the page over here. So on top of this region R, you will have infinitely many squares sticking out of your screens as your cross sections. And I hope you can imagine how the solid will look like. So if you have a cross section, if you have a vertical strip here, there is a corresponding square that will stick out of the page. So basically you can imagine the solid to be infinitely many thin squares that are stacked very close to each other, thus producing a solid. Okay, can you guys imagine that? I will rely much on your imagination over here because I'm not good at drawing those objects. But I hope you get the picture. Is that good? All right.
I imagine like a blob of jello. I don't know why.
Yeah, exactly. Something like that. So you have your plate as your base. And then on top of that plate, you will have jellos that are squares in shape, right? And then the idea is, how do we get the volume of that solid? Well, you can imagine that solid to be formed by infinitely many squares that are stacked together. So basically the volume or the amount of material, as they say in physics, that is needed to construct your solid will just be the summation of the areas of those squares that served as the building blocks of the solid, right? But the problem there is there are infinitely many squares and they are closely packed to each other just to create the volume. So a summation of the areas of those squares will not be enough because they are squares that are very, very thin that are placed next to each other. So that's why instead of a summation, we do integrals. Remember, integrals are the infinite and continuous versions of summations. So that's why the formula for the volume of such solids are represented by the integral of the areas of the cross sections. In layman's terms, this is the continuous summation of the area of those cross sections. And the idea is that the amount of material needed to create that solid is just the summation of the areas of those cross sections that we stacked next to each other. There are infinitely many of them. That's why we use integrals. And I hope that clarifies or that gives some sense into why we have this formula in front of you. That's the thing, because usually formulas are easier to remember if you know the reasoning behind them. So basically integrals are continuous summations. So the volume is just a continuous summations of the cross sections, right? Because of that idea of how this solid would be formed. Okay, and with that intuitive notion, let's try to look at some specific examples. So let me scroll up and copy paste problem number 10. I hope that made a little bit more sense than just looking at how the formula looks like and just memorizing it for the sake of computing things. I usually want to go behind the formula, why is it so that it's easier to remember. Okay, let's do problem 10. So here, the solid of the base of a solid is the region bounded by the circle x squared plus y squared equals 9. So basically, I'll draw a picture here quickly. Okay. Remember, x squared plus y squared equals 9 is a circle centered at the origin of radius 3, right? If you remember your conic sections. So I'll have a negative 3 here, 3 here, negative 3 here, and 3 here. Then I'll have a circle. Imagine that's a perfect circle. And then this is the base of our solid, the base of our solid. And then what's next? We were told that the cross sections are perpendicular to the x-axis. So that tells me, okay, the volume will be an integral with respect to x. Because again, the cross sections are perpendicular to the x-axis. Now, knowing that I am integrating with respect to x, I need the bounds for x. Of course, you could use some symmetry over here, but I'll forget about that for a moment. Let me do the entire integration without assuming any symmetry. If I look at the shaded region, it started when x is equal to negative 3, and it ended up when x is equal to 3. So the bounds for the integral would be from minus 3 until 3. And then the cross sections are squares. So here I will have a vertical strip because I'm integrating with respect to x, and that vertical strip will correspond to a square that sticks out of the screen. Okay, so basically that's how the cross sections look like. So they are squares that are sticking out of the screen that is drawn on top of this circle. So I hope again you can use your imagination to picture this out. Now, if we follow this idea, the solid is formed by superimposing or stacking together infinitely many squares lying on top of the circle, right? So if I have a vertical strip here, that corresponds to another square. I do that infinitely many number of times, I'll get my solid, right? And that tells me to get the volume, I just need to sum up the areas of those infinitely many squares. But what is the area of these squares? Well, remember the area of a square is side length squared. But what is the length of a side here? Well, the length of a side will just be how long is this guy, right? Maybe I should erase the other, okay, the other square. So basically what we do is, okay, the side length S would be this length over here. How long is this strip? But remember, this is exactly the vertical strip that we drew. And remember from last time, to compute the height of a vertical strip, that would be the top function minus the bottom function, right? But what are these functions? Remember, we are dealing with a circle of equation x squared plus y squared equals 9. And then I solve for y in terms of x. I'll get y squared equals 9 minus x squared. And then y is equal to plus or minus root of 9 minus x squared. Good. Now, why do I have two options here? Remember this top portion? That is the one that has an equation y equals root of 9 minus x squared. And the bottom half of the circle, this guy, that has equation y equals negative root of 9 minus x squared. Okay, so that means S. Okay, so S, the side length would be top function minus the bottom function. So that will be root of 9 minus x squared minus negative root of 9 minus x squared. So that will be twice of root 9 minus x squared. All right. And then remember the integrand would be the area of the square, which is s squared. We already know that s is equal to this. So the integrand over here would be 2 times root of 9 minus x squared quantity squared. All right. Or if you will use symmetry, which is perfectly fine because we know that the circle is symmetric with respect to the y-axis. Well, what you could have done is to integrate instead from -3 to 3, just integrate from 0 to 3, same integrand, but multiply it by 2. Right? Because the volume will be the volume of the right hemisphere times 2, or the right semicircle times 2. Right? And since if you look back at the problem, it asks for the actual volume. So you need to evaluate the integral, which is which is easy because remember, you still have something squared. So the square roots will be gone. If you carry out the calculations, I guess the answer would be, I calculated it beforehand. The answer is 144 cubic units. Okay.
Excuse me.
All right. Yeah. Go
Can
ahead.
you explain one more time why you changed the boundaries?
Okay. For the second integral.
Yes.
Well, the only reason why I do this is perhaps you might want to use symmetry, because remember that the base of your solid is all over the entire circle, right? From -3 to 3. Probably you notice that, oh, the circle is symmetric with respect to the y-axis. So I can just integrate from 0 to 3 over here, this shaded region, right? And then compute the volume, which is this guy, but multiply the result by 2 because I have another half here that I didn't include in the integration. So yeah, so you can use this. I only did this if I want to take advantage of the symmetry. Of the symmetry of the circle. But it's perfectly fine if you don't want to take advantage of the symmetry. You could have just left your answer this way and then just forget about this. If you don't want to take advantage of the geometric symmetry of the shaded region, which is perfectly fine. Anyway, you'll get the same answers once you compute those integrals. So maybe that could cause some confusion. So maybe I'll just cut this out. Okay, is that fine? So it's up to you if you want to use symmetry or not. But rest assured that if you had the right setup and you evaluated the integrals correctly, then you should get the same answer.
Okay, thank you.
All right, any other questions? Okay, none. Let me try problem 12. Hold on, let me scroll up. Okay. I'll skip problem 11. I'll leave that to you guys, but I'll include the solution to that in the next update for the worksheet. Well, it's the problem 10 and actually problem 11, because here the cross sections are again squares perpendicular to the x-axis. So your solution would be similar to problem number 10. The main difference with problem number 10 is that the solid is bounded by a parabola, or the base is bounded by a parabola, but that is similar to what we have in problem 12. So you can pick up the bits and pieces of our solutions from problems 10 and 12 and then to come up with your own solution to problem 11. So try problem 11 on your own, compare your answer with the one that I will upload later today. So yeah, that will be a good practice. Okay, let's do problem 12. Okay. Okay, so what do we need to find for problem 12? Problem 12 simply asks for an integral that gives the volume. So we don't need to calculate the volume. So once you have the integral, do not evaluate it unless you are specifically told to do so to save time for, say, exams or quizzes. So I take note for problem 12, I only need the integral. No need to evaluate, right? Now, what is the base here? The base is the region bounded by this curve. Faiza is asking a question. Will the problem always indicate what shape the cross sections are? Yes. The problem should tell you what the cross sections or how the cross sections look like. It should give you the position relative to the x or the y axis, and it should also tell you the shape. Usually for Cal 2, we only deal with squares, semicircles, and I guess sometimes equilateral triangles. So yeah, those are usually the three basic shapes that you need to remember. Okay, going back to the problem, the base is on the first quadrant, bounded by the parabola 9 minus x squared. 9 minus x squared is a parabola opening downwards with vertex when x is equal to 0, giving us y equals 9. Okay, there we go. And then the point of intersection here, when y is 0, x is equal to 3. Okay. Maybe I'll put the 3 over here. This is x equals 0. This is the region R. Okay. And then we were told next that the cross sections are perpendicular to the x-axis. So that means I know that the volume would be in terms of the variable x, because the cross sections are perpendicular to the x-axis, right? So my bounds would be bounds for x from the figure. I already figure out that the region will start at x equals 0 and will end when x is equal to 3. And then what's left to be determined is the integrand. But the integrand, remember, is the area of the cross sections. The cross sections were said to be semicircles. So we need the formula for the area of a semicircle. But that is nothing more but half the area of a circle. Circle has area pi r squared. We are dealing with semicircles here, so it's just 1/2 pi r squared. And how does those cross sections look like? So they will look like this. Semicircles sticking out of the screen. So that's how our cross sections look like. Okay. And then now, how do we find the area? Well, if we look at this rough sketch here, the length of the strip tells us the diameter of the semicircle, right? And the diameter is basically the height of our vertical strip. Now the vertical strip, again, this is top minus bottom, right? The top function corresponds to the parabola 9 minus x squared, minus the bottom function is the graph of the bottom function is the x-axis, which is the line y equals 0. So that's why I have a minus 0 here. So that's 9 minus x squared. But be careful here, that's the diameter. So the radius would be half of that. So that's going to be 9 minus x squared all over 2. So that's the formula for the radii of the cross sections. Okay. Then I'll just simply plug that into the formula for the area of a semicircle. So it's going to be 1/2 pi times the radius. So that's 9 minus x squared all over 2 quantity squared. Then let me simplify a bit. This would be pi over 8 times 9 minus x squared quantity squared. So that's the area of the semicircle. So I'll just use that as my integrand here because we get the solid by superimposing or by stacking together infinitely many semicircles with area pi over 8 times 9 minus x squared quantity squared. Basically, I'll have this. And since the problem is just asking for the integral, I don't need to evaluate it. So that's going to be my final answer. And I won't spend time evaluating this integral because the problem is not asking for it. All right. Any questions? Any violent reactions? You guys are very quiet.
Can you explain that how you got the area again, like the pi over 8?
Okay, so let's see. So I got this first step by just taking half of the area of a circle because we are dealing with semicircles. And then is it clear how I got this? This is the radius, right? Coming from our analysis over here. Okay. And then I got the pi over 8 by doing algebraic manipulation because here I have 2 in the denominator, but that should be squared. So I'll have eventually a 4 in the denominator. And then there's a 2 outside. That's why I got the 8 over there. Pi is copied over. And then 9 minus x squared quantity squared is just the numerator over there. Okay. Now, if you want, you could have just copied this entire thing into the volume, into the integral, and that's perfectly fine with me, right? Even if you didn't do the algebraic manipulation to pi over 8 times 9 minus x squared quantity squared. And I hope you guys see the utility of sketching at least a rough picture of the problem. So you can from there analyze how the figure looks like, how the strips are related to the area of the cross section. So it would be easier to compute what's the length, what would be the diameter, and so on. Okay. Any other questions? You're probably still hangover the weekend, so any other questions? If none, then I have a question for you guys. So there's still one more problem for cross sections involving or for volumes involving cross sections, problem number 13. Do you want to go over it, or let's go to solids of revolution?
Wait, what?
Yeah, I have one more problem about cross sections in the worksheet, a very similar one to problem 12. Do you want to go over it, or should we skip that and then let's go ahead to the next topic, which is about solid subrevolution?
I don't know what the second one is, so
Mm-hmm. But there are no other questions about cross sections, or cross sections kind of easy for you? Do you get the general idea?
I mean, the only question I have is the only reason you didn't expand that polynomial is because you weren't asked to evaluate it, or would you
Uh-huh.
expand that if you were like, would you leave it like that if you were asked to evaluate that?
If you were asked to evaluate this, then you need to expand it because you cannot do a u substitution for this integral. So you will be left no choice but to expand the 9 minus x squared quantity squared into a trinomial and do the integration term by term.
Okay.
So that's why it's important to take note what the problem is asking for. If it's just asking for the integral, then you don't need to calculate anything. You don't need to expand anything as long as you can set up the integral and the integrand properly, then no need to show off your algebra skills. But if the problem is asking for the actual volume, then you need to expand everything, simplify everything, compute for the integral. Okay? So, okay, no other questions? You're exceptionally quiet today, but okay. I hope that's fine because most students find this easy. The only challenge here is actually determining the formula for the cross section, for the area of the cross section, which I guess you can find by having a rough sketch of the region, identify what its parts and how the strips are related to the parameters of your shape, be it the side length, be it the radius, and so on. Okay. Now I'll go ahead to solid subrevolution. My problem with solid subrevolution is that you just finished the disk and washer method in the lecture today because I was planning to consider a solid and then set it up using both cylindrical shells and disk or washer method. But you haven't discussed cylindrical shells yet, so I don't want to preempt the lecture. So I'll just stick to disk or washer method for now, and then go back to these examples again on Wednesday and set up the integral that will give the volume using cylindrical shells, right? But the general idea is this. What would be given here? You will be given the functions that will give you a shaded region, right? So suppose you're given those information, and then say your shaded region looks like this, for instance. Okay. So shaded region, y equals f of x, y equals g of x. Then aside from the region, you will also be given the axis of revolution. I'll call the axis of revolution AOR for short as I write the solutions for this. For Cal 2, it's either a vertical line or a horizontal line. So basically say the axis of revolution may be something like this. Okay. So this is x equals a. This would be our AOR. And the idea is you will revolve the region about this axis of revolution. So you will revolve the region R with respect to x equals a. So imagine having the solid at the back and pointing out of your screen. So you'll have that solid. And the volume for that solid can be computed using either two methods, using disk or washer method or the cylindrical shells method, right? But the idea is this. Oops. I usually start by picking out what type of strip to use. So if you use if you use vertical strips, then you always have a dx. So your integral would be with respect to x, or bounds would be with respect to x. Your integrand will be expressed in terms of the variable x. If you use horizontal strips, then you will use dy. So you integrate with respect to y, bounds would be for y, the integrands will be functions of y, right? And nothing new about this. This is the same thing that we agreed on when we discussed areas, all right? But the method to be used depends on the position of the strips with respect to, so I'm going to use WRT for with respect to the axis of revolution. If your strip, right, are perpendicular to the AOR, so it makes a 90-degree angle with the AOR, then you will use the disc or the washer method. But if your strips are parallel, I'll use the double line to denote a parallelism between two lines. So if the strips that you will use are parallel to the axis of revolution, then you will use cylindrical shells. Yes, any question?
So are we integrating two functions here?
We'll only integrate one function, but that could be a combination of f and g, depending on how the radius or the height will be computed. I'm going to show later how to do this, but I'll start always by having it clear what are the strips to be used and what would be the particular method to be used. But I guess for now, we will be limited to the disc or washer method. So the strips that we will use will always be chosen to be perpendicular to the AOR. But when we do the discussions on Wednesday, we can also use cylindrical shells. So we will be able to use strips that are parallel to the AOR. Okay. And probably it will make more sense if we consider some specific examples. So let me go to, yeah,
Sorry.
go ahead.
The AOR is just the axis that the shape is around?
Yes,
Okay.
that's the axis with respect to which you need to revolve the region to get your solid. Okay.
Thank you.
So let me copy paste problem 15. Yeah, hold on. Okay, so let's have draw the region first. So the region R is in the first quadrant, bounded by these two curves. So okay, sketch the region. Y equals x is just a straight line passing through the origin. Y equals 8x, and then y equals x cubed is the cubic function. Y equals x cubed. And then I need to solve for the points of intersection over there. So let's do that. So that we know what are the bounds for the integration that we will carry out later. So for the POI, we just equate the two expressions for the functions together. We have 8x equals x cubed, and then this would be x cubed minus 8x equals 0. Factor out x, get this. Then that means x equals 0, or x squared equals 8, which means x equals plus or minus root 2, right? But since we are just on the first quadrant, then I can just drop the negative root and say that x is equal to positive root of, sorry, not root of 2. This would be 2 root 2. Because I will have root of 8, and then root of 8 can be written as 2 root 2. Okay. Now, if x is 0, then the corresponding y value is 0. Then if x is 2 root 2, then y would be 16 root 2, right? How do I get 16 root 2? Well, I know that y is equal to 8x, so I can just plug in x equals 2 root 2 to get its y value. So basically what it says here is that here, this is 2 root 2, and then here, this is 16 root 2. Good? So at least now we have a basic understanding of how the graph looks like, or how the shaded region looks like, okay? Which is important. So we go to problem A. For problem A, we have the same region, or we have this region. The AOR is the x-axis. So the AOR is the x-axis. So the shaded region, or the solid, will be formed by rotating the highlighted region with respect to the x-axis. So you'll get some sort of a cone with some curvy inside, right? I guess that's the best way I can describe it. So I hope you can imagine it. So basically like a cone, but the inside will have some curve. So yeah, that would be the shaded region. Now, since I only know, we only know for now how to compute for the area using using disk or washer method, I will choose the strips to be perpendicular to the AOR, right? So maybe I should note that here to use disk or washer. The strips should be perpendicular to the AOR. Right. The AOR is the x-axis, which is horizontal. That tells us that we need to use vertical strips. Like this one, right? In order to use the disk or the washer method, right? So since we are using vertical strips, we know that vertical strips are always associated with a variable x. So I have that there. And then I need the bounds for x. Luckily, we know what the bounds for x are. The region started at x equals 0 and ended up at 2 root 2. Okay. And then for the disk or washer method, there's a pi multiplier here, because what will happen is it would be a stack of infinitely many circles that are closely packed to get the volume or to get the solid, right? So that's why you integrate the circle or the area of the circle pi r squared. But this is a little bit different, because if you imagine getting the solid, would you agree that there would be a hollow or an empty space for the solid? If you rotate the solid with respect to the x-axis, you will form some sort of an empty space in the interior of the solid, right? So it's basically like an ice cream cone with a curvature in the inside, but nonetheless, there would be an empty region inside, right? Another indication that there would be an empty region or a hollow inside your shaded region is that if you draw the vertical strips coming from the AOR towards the end of the region, this is like what I did here. Notice this part. That part over there is not on the shaded region. So part of the vertical strip that I am using here doesn't lie inside the shaded region. And that's an indication that you will need to use the washer method. So here we're using the washer method. Exactly, because there is a hollow in the solid that will be formed, right? So for the washer method, your integrand would be pi times outer radius squared minus the inner radius squared, right? That would be the integrand. Now, what would be the outer radius? Well, the outer radius will be entirely this. That's the biggest. That's the bigger radii in this picture. So I have that vertical strip coming from the AOR towards the end portion of the region. Remember, the radii are always to be computed from the AOR. So the larger one will start from the AOR, from here, and it will end until here. But that end corresponds to the straight line, right? Remember how we calculate distances in the Cartesian plane? It's always the top function minus the bottom function. The top function here is 8x because the endpoint of the outer radius lies on the straight line. And the bottom function is the x-axis, whose equation is y equals 0. So that means the outer radius would be upper function minus lower function quantity squared, right? Minus, since I'm using the washer method, I need to subtract from it the inner radius squared. What's the inner radius? The inner radius is this guy, the smaller of the two radii. This is the radius coming from the AOR until the cubic function, until the red curve over here. The inner radius, as you might have noticed, represents the length of the strip that lies outside the shaded region. So remember, I drew a vertical strip earlier. This vertical strip was drawn earlier. I noticed that part of it, which is exactly this guy, lies outside of the shaded region, and that corresponds to the inner radius. Basically, the idea is to compute the volume as if there was no hollow, and then subtract from it the volume of the hollow. That's why you had the formula outer radius squared minus inner radius squared. And again, how do we compute the length of that strip? Or how do we compute the inner radius? Well, it's the top function minus the bottom function. The top function is x cubed minus the lower function is the x-axis, which is y equals 0. So I have this. So basically, if I simplify this, it would be 2 root 2 times pi times 8x quantity squared minus x cubed quantity squared dx. And that would be the integral that will give me the volume of the shaded region. Okay. Oh, it's already 12:53. I didn't notice the time, but do you have any questions about this? Any clarificatory questions? Don't worry, because we will devote Wednesday's meeting for more examples on this, using the disk washer method alongside with the cylindrical shells method. But so far, any questions? Yeah. And I usually discuss it along with the geometry so that you will have a visual way of inspecting the lengths that are involved in the problem. Yeah. So the points of intersection are computed this way. So the idea there is you put those two equations together. First graph is 8x, second graph has equation x cubed. Just put them equal to each other. Then how do I get the integrand? Remember, the integrand is outer radius squared minus inner radius squared. So I basically measured what is the outer radius. Well, the outer radius is coming from the AOR towards the uppermost portion of the region. That's why I had 8x minus 0 squared. And then I have the inner radius squared coming from the closer curve to the AOR until the AOR. So that's why I got x cubed, which is the red curve, minus y equals 0. That's why I got x cubed minus 0 over there. Don't worry, Jocelyn. I'll go back again. When we go back on Wednesday, I'll explain this more in details. Right. So just try to, if that didn't make too much of a sense right now, probably I went too fast. You can rewatch the last portion of the recording, or I will discuss this again on Wednesday. Some more examples of this on Wednesday. Okay. All right. So sorry, I took 5 minutes more than intended, but I hopefully this started to make sense, just like what some of your classmates said. So on Wednesday we'll work on more examples like this, and then we'll do it side by side using disc and washer method together with cylindrical shells method. So you get acquainted with both methods. Okay. But I hope you remember this bits of information over here. We will need this for next time. Okay. All right. So thank you guys for coming today. I hope you enjoyed the rest of the day, and let's see each other again on Wednesday. Bye.